if you read Jonathan already, like he has a blog post from 2020 about the Ethereum supernova and the fragmentation problem within Ethereum, and how he was thinking that it might be unsolvable. And he was convinced it's possible. I was exhausted. We kind of had this whole year, like if you I'll take you back 6 months ago or 5 months ago.
Supported by Kaspa Finance, the first V3 DeFi protocol on Kaspa. Igra Labs, atomic programmability on a Kaspa blog DAG.
Great to see you again, Ankit. How are you?
Good. Thanks. Yourself? I'm sure it's been busy times for you. But Michael, for today, our topic is vProgs ins and outs. And my aim for today is to simplify vProgs so that each and every person, within the Kaspa community and perhaps the wider crypto community understand what vProgs are and how vProgs are an improvement over traditional smart contracts. Just a side note, we're not going to discuss DAG night, and we are not going to discuss zero knowledge circuit part today for this session. So let me start by asking, how do you simply define vProgs to someone who's brand new to it?
I'd say vProgs are an attempt to use zero knowledge technology to create a one-dimensional flat space of programs which can synchronously compose with each other. I mean, they can create a single transaction touching multiple state accounts from multiple programs, while still remaining separate entities with some sovereign properties. They're kind of independent in the way they waste or use resources, and in terms of the state they need to know about each other all the time. So it's trying to balance a line between sovereignty of programs, having them as independent units, and still being able to speak to each other. And the main factor enabling this sync composability is the fact that they all share a single sequencer, which is the Kaspa L1.
Right. All right. Lots of complicated stuff for someone who's brand new to it. So can I try to simplify it? So basically, smart contracts using zero knowledge proof, but designed specifically for Kaspa.
Yeah. So I'd say every discussion about vProgs should start from understanding what a base rollup is, probably.
Right.
Perhaps. So we can say a few words on that, if you think that's necessary.
They are tiny base rollups, right? If that's the right way to put it.
Tiny base rollups with where L1, where a significant effort is being made and will be developed to add L1 components, which are the minimum required to allow these programs to still somehow magically compose with each other, even though there's standalone ZK units. So yeah,
right.
But if you start from a base rollup, so we look at Kaspa as a scalable, in a sense, data in terms of data throughput L1. So we're allowing ourselves to design a system where all transactions appear on L1, even though they appear just as a payload. For instance, L1 is not going to execute the transactions themselves, and it's not going to maintain the state space of the programs. So L1 is sequencing and making the data available, and it also provides a settlement service where it verifies ZK proofs and allows an L2 entity to advance its state commitment reported to L1. Yeah, so that would be like a base rollup. Just a comment on that, like it's common in the ETH world to speak about data availability, sequencing, and settlement. And you can easily speak about systems where availability and sequencing is done by some sidechain or some other consensus or a centralized entity, while settlement happens on Ethereum. And there's a price to all this. Like, if you think a base rollup having all roles in the same L1 is obviously the more sound approach, because obviously it's easier to prove to the L1 I was following your sequencing. L1 is well aware of how it's sequenced. It doesn't need any attestation to the sequencing. It can actually look at itself, see how it committed to the sequencing, and make sure the ZK proof actually proofs that it followed this sequencing. While if you let another L1 or another L2 sequence, you have to somehow provide proof between consensus. You have to introduce some trust, even though it's minimal. Like, it's not easy to verify different consensus, unless it's a closed set of validators, maybe, and then you can have an easy, maybe multi-sig check or something like that. But so having all these roles on a single consensus means that the L1 is the sequencer. It orders, cannot, no one can censorship, and it kind of inherits the security of the L1. Okay, so you have this entity of a base rollup, which is using the L1 for sequencing, and it's going to prove everything all the transactions to the L1 that it's going to prove that they were all executed correctly. And the state transitions from some previous state to this new state. So you can have many of these, but they each are a silo in a sense. They each follow the sequencing of transactions targeted to them and prove to L1 that they have executed all the transactions targeted to them. So that's, say, a few islands of L2s, which can each use the same L1 for as a based sequencer. What happens when they want to communicate to each other? That's where it becomes challenging. So one obvious way to communicate is through asynchronous messages. Once I proved a state transition, I can use my proof to attest to some kind of internal state of me and send this kind of a message to someone else with a proof to my previous proof linking, with a witness proving linking to my previous ZK proof, and I can and then he can operate based on that information. So that's what you would call asynchronous messaging. But that still doesn't give you the ability to compose within a single transaction in an atomic way. Like, you want to do something that touches multiple contracts and states and perform one single operation or not. So what we're not using, and stop me if I want to add a point before. We're not using the fact, if you just look at base rollups, which are asynchronously sending messages to each other, we're not using the fact that they all are sequenced by the same sequencer. Like, each one of them is using the L1 for sequencing his own subset, but the subset of these transactions has no relation. So we're not using the fact that we actually have one canonical order. But if you think about it, we do have one canonical order. So, and that's very powerful, because if we have one canonical order, we actually have one consensus for the entire global state. Even if it's fragmented, even if it's siloed, there's every point in time, you can attribute a point in time to each transaction, right? So for every point in time, we actually have a deterministic, a well-defined state of the entire L2 space. And that attribute can be used to conceptually create synchromposability, because if there's a discrete state while executing a transaction, it's very clear deterministically what's the state of all others. You can actually imagine a design which uses this to actually read from multiple places and actually compose logic.
Mm.
So that's like the opportunity, I'd say.
Ooh, Michael, you touched upon so many, I think, broad topics. I think from Ethereum ecosystem, on how messaging happens, to base rollup. I guess the way people define base rollup, and then obviously you've touched upon also the layer twos on Kaspa. Let's call them right. How things perhaps people think about base rollups. But can I, if you don't mind, I want to pull you back a little bit, and I want to go step by step. And then
let's break it down.
Let's break it down. Let's pull all the sort of threads so that people understand, what these things are, and then perhaps we can wrap it up towards the end again. So vProgs, right? I mean, if you come from Ethereum world, if you know Ethereum, right, EVM is all happening on chain, right? All of that happens on chain across the nodes. So some people might jump and say, aha, right? It's off chain, means it cannot be trusted. How do you answer those people, and what's your take on that argument itself?
It's about understanding what ZK technology, or the more accurate term is validity proofs. So essentially, this cryptographic wonder is a tool to deterministically and sufficiently strongly proof that I actually executed like when you call a smart contract on Ethereum, you sign your transaction calling some smart contract, right? So why do you do that? Because you know this smart contract has a hash, and you verified either socially or by your own eyes that contract has logic that doesn't steal your money, but actually will swap for you a token with another. Okay, so you know that contract is sound, meaning it doesn't take funds from people. It just it goes by specific rules, takes like the exchange ratio and performs the swap. And then you call that contract with some kind of ID and you sign it, so you're good. So same thing would happen here. You would sign a transaction calling a specific program, and the ZK prover would have to execute that program, which is encoded in this hash, in a similar way to what I described, in order to advance the state on L1. And it's going to advance the state on L1 in a succinct way. It's not going to, L1 doesn't know the full state, but L1 knows like the Merkle root of all the state, or some kind of commitment. And the prover is going to tell the L1, okay, you can advance the state from this state commitment to the following state commitment because I'm showing you that I executed the program correctly. And that's the updated root. And then obviously someone else can show you versus that root, like what's your updated state within the actual state tree. But the ZK prover actually proves exact execution, just as if an L1 executor would execute that contract for you.
Yeah.
Was I answering the question?
No, I think you are right. And one analogy I was thinking was it's similar. ZK proofs are similar to tamper-proof seal a letter. I don't know if you like this analogy, but like, in the old days, at least, you used to have the tamper-proof seal, and then you trust the content without reading every word because of the seal. So I think of that, like ZK for me has been that type of technology where, you can trust the seal, and that lets you sort of verify the correctness on chain without.
Yeah, it's worth mentioning that ZK itself is a kind of slightly misleading originally in this context. A more accurate term is validity proofs, because we don't use the zero knowledge attribute of these proofs.
I see. And so when you say you don't use the zero knowledge proofs the better term is validity proof. What does that mean?
Zero knowledge proof means originally in cryptography, when you're saying I provide a zero knowledge proof for something, means that I can prove to someone that I solved some problem without leaking any information about how I solved the problem. So obviously, if I share the solution with someone, say, think about a graph problem, like some computational problem, someone is asking you to solve an exponentially hard problem of graph coloring. And you have a solution. So if you provide the solution, anyone can verify it in linear time. It's very easy. But you want to show someone you have a solution without leaking the solution. The solution is precious to you. I don't know. So that's where zero knowledge, that's where that terminology comes from. And in blockchains and proving valid computations, we don't really care about not leaking how we computed those programs. Anyone can compute those programs. It's a public knowledge. So there's no real caring about that zero knowledge non-leaking part. That's related more to privacy technology.
I see. So the leaking part could be the transaction, the balance, the addresses, like those are the parts that in this case we don't care about.
Yeah, I'm not an expert, but I think that the fact that the zero knowledge proofs for validity proofs don't need to avoid leaking information must simplify the cryptography in one way or another.
Right. Okay. I did say we're not going to discuss ZK part, but here we are.
Yeah.
Apologies. But yeah, that's okay. That's great. I think we can perhaps come back if people have more questions on ZK specifically. So then I guess the obvious next question would be, why choose vProgs over EVM or perhaps even over other traditional virtual machines, right? Many other blockchains have ended up building their own VMs, right? Why to go down this route?
vProg's ambitious goal would be not to choose a VM. Actually, it's saying like each vProg can actually be built with a different style of VM. It's not so easy to support many technologies, and also I'd say that vProgs have merit even if you choose one technology, because the sovereignty versus composability attributes are relevant also if it's exactly the same technology. You can still, even if you know exactly how to execute all programs, it's the same interpreter or the same VM, and etc. You still don't want necessarily to execute all other programs. So that's the sovereign part of execution.
Yeah.
So I think the technology stack and infrastructure is kind of orthogonal or independent to the vProg design. Obviously, vProgs are going to come with one or two selected VMs at first. Hopefully two, because we need two would already bring the flavor of not being one, and would already introduce enough challenges. So I think hopefully two, but once you have two, you can have more. There's a question of how to allow more systems to enter it. So initially, I'd say it's kind of a whitelist. These technologies were audited and verified, and everyone in the system knows they follow the specification correctly. So we can compose with them because they follow the same protocol. In a future world, you can imagine maybe verifying somehow equivalence of. It's out of my current bounds, but there is a future thinking of but let's get to
so there could be different
first.
But there could be different VMs essentially across different vProgs, right? That's the aim here, to have EVM versus Rust, or like different people running different VMs.
So EVM itself would be slightly not natural for vProgs, but it possibly can be adopted as an infrastructure, but it should still adapt the thinking of contracts as a unit, as a provable unit, with a dedicated covenant on L1, and not like group many contracts under one executor.
I see. Yeah, I see what you mean. Yeah.
Because that's kind of the idea, a one-dimensional space where progs only compute each other when they need to, but they can still compose. So
right.
I'd say you can somehow adopt EVM as a template for each prog. That's how I see it.
Yeah.
I see the infrastructure more as a template. Think about a program deploying, wanting to build a smart contract. So it can choose, ideally in the future vProg world, it can choose a template. Okay, I want to go with Solana style ELF contract prog. So I'm using Rust and I'm building like a Solana-like program. And there's a specific prover network that knows how to prove my program, etc. So, or either I want to write it in Solidity or another language. So I can kind of use a template from a few options, which might be developed by multiple entities with various interests. But it's more like a template and not going into a group of contracts logically, but more choosing the infrastructure template.
Yeah. I think that's the reason I asked. Like, if a developer wants to build on, coming from Solana ecosystem and they want to build on vProgs, like they have a way via these templates perhaps to build, or someone coming from like Ethereum knowing Solidity, right? They can all build on vProgs using their own VMs essentially, right?
Right. So EVM would be less natural because the way vProgs are designed, you have to explicitly say what accounts you're reading and writing to, and there's kind of that progs themselves are stateless. So it's not like it's not by chance that it's Solana inspired in a sense. What Solana did maps naturally because Solana was thinking about programs as kind of black boxes. Okay, so a black box, a stateless black box, which can obviously there's accounts that only this owning program can write to. That's where it can maintain its state. And every transaction declares exactly what it reads and what it writes to, which allows building some kind of computational DAG. Get to that. And programs wanting to call each other cannot assume compiler compatibility or stuff like that. They have to actually serialize their call. So in that sense, that's where you can see the black box. So a program doesn't know much about another program except for this convention of how to call it and how to serialize data, and then the callee would deserialize according to its convention. So they did it for conceptual, philosophical reasons of they wanted a more low-level program-oriented system. That's my understanding, as well as all kinds of performance considerations. And it happens to be that ZK fits to this more naturally, if you want. That's why we also called it verifiable programs and not verifiable contracts. It's kind of more of a program, and it's a verifiable one. And it's the same in the sense that each program wants the transaction issuer to declare the read writes, so it can know if it's composing, what it needs to know about others, etc., etc. So you need the static information of these dependencies. And when you call another program, the same black box idea applies. You sometimes, we can get into that, but there's at proving time, there's kind of a magic. You don't really call the other program. You kind of condition on what it would say.
I see. I think I'm starting to get an idea. But also it's sort of bringing a lot more questions. It's
Yeah.
it's just exposing a lot more things and a lot more stakeholders, like prover you mentioned, which is perhaps a new terminology to a lot of people. But I want to get to that part. But would you say vProgs will be, everyone has been wanting the smart contracts on layer 1.5. There's been a big debate. Base rollup is layer 1.5. Do you think vProgs is fits somewhere between, or is it considered to be 1.5, 1.25, somewhere even better, or is it layer? I mean, it's not layer 1. Where do you think it sits?
So I'd say layer 1 is when you execute on L1, probably. The intention here is that L1 remains the hub of progs. You deploy them on L1. Obviously execute them not on L1, but because they're atomically and synchronously composable.
Mm-hmm.
The experience should be as if they are on L1. That's like the user experience and the dev experience. The aim is that it should be like this unified space. And in that sense, you want to say they are L1.
Right.
They are very native. Like L1 is doing a whole lot of effort to maintaining information so that they compose. Okay, so the fact that L1 technically isn't executing, it's still doing so much to create this unified one-dimensional space where everyone can interact with each other. So hopefully it creates the feeling of an L1. Yeah. And obviously we want the unified liquidity. So it's a part where it might be challenging to create the feeling of an L1, and that it seems like at the very least you have to bridge. So if you think about it, atomic composability, it's always mentioned in regarding to unified liquidity, right?
Mm-hmm. Mm-hmm.
So how's that going to work? So once you have atomic composability or synchronous composability, you can think about an asset hub. So think about a standard special program, which implements most token management, minting, and stuff like that. So the Solana has an SPL, which it does exactly that. So this standard program, and so there's one single liquidity space or entities, and everyone can compose with it. That's where you get unified liquidity. What you must still solve is bridging from L1. If you want to bridge Kaspa to the L2, you still have to somehow move it to the L2 space. Even if it's a unified one, you'll still have to do some kind of bridging. But if we do enough effort in terms of standardizing stuff, standardizing stuff, and kind of use the same Kaspa address maybe, and use the fact, for instance, think about small stuff which can be significant. Like if you sign a transaction on L1, so you're signing the inputs. So if you essentially you're proving also to the L2 you're authorized to use these addresses that happen to be the L1 UTXO addresses. So an L2 can look at this and say, okay, this transaction was signed by this address. L1 verified it. I don't need to verify a signature of this signee, for instance. So if the address space is somehow unified and there's a standout of looking at specific address across layers, and it's a bit too early to like discuss the details because we need a lot to go before that, but I'd say that the intention is to somehow create the most unified experience even across the L1, L2 boundaries.
Yeah. How do you quickly define liquidity in this context? Because when I was thinking, and perhaps for most people, liquidity is more in the context of money. People think of liquidity is like this, like let's call DEXs, where if you have Uniswap across Ethereum on layer 2s, you'll have on Optimism, you have on Base, same Uniswap, but then you'll have different liquidity sitting on, Optimism, different liquidity sitting on base, but that's not what you're defining liquidity here. It means something different in the context of vProgs as you're defining it.
Means that that's what I mean when I use the term one-dimensional, because if you have a two-dimensional space where apps are within a rollup entity like Base, Arbitrum, and others like Ethereum, if you're an app, you benefiting from the fact you can compose with different entities, with different other contracts on your specific rollup. And you actually, I don't know, you loan against some kind, or you provide liquidity from your token to some swapping service or some DEX. That if you would want to compose with a different app sitting on Arbitrum, you'd have to move your app to that place and make sure you have the same kind of services and liquidity. You're kind of tied to this bundle. So the two dimensions create an unsound space where you're not free to, it's not a zero-sum game, or it's not a healthy competition between applications, but applications have these constraints that come from the fact that they're part of another bundle, and the liquidity doesn't necessarily move easily between two rollup entities.
Yeah. So this is where that synchronous composability part is such a key part, right? Because that unifies the liquidity across.
You can't speak about a single asset hub without allowing composability with it.
Yeah. Can I ask some very little bit of personal question? I want to focus on technology, but just quickly, when did this whole vProgs idea kicked off? When was it? When was the aha moment that, okay, this is what it's going to be? Perhaps the architecture. When did it start, and who are the sort of brains behind it so far? Who's been working on it?
I'd say so. There's the necessity or the need for it, or the defining the ambitious goal. There was like the main moment where, okay, this is how it looks like. So if you read Jonathan already, like he has a blog post from 2020 about the Ethereum supernova and the fragmentation problem within Ethereum, and how he was thinking that it might be unsolvable because Ethereum reached this fragmented state. It cannot, even whatever effort you do, there's too much interest already, and you cannot redesign the system and fix it. So he wanted to do it correctly on Kaspa from the set out. And the reason for believing it's possible was, like I told you, the single-based sequencer for everyone, which creates the possibility to even imagine that.
I see.
And he was convinced it's possible. I was exhausted. We kind of had this whole year, like if you I'll take you back 6 months ago or 5 months ago. We wrote like several research posts on Kaspa research, and explaining and building a prototype for base rollups, essentially. Because we knew we can't jump into, even though atomic composability was a goal from the start, we had to understand what the units are, how you start building a base rollup over UTXO based system like Kaspa. That was like the first. Let's figure that out first. And then I think I was somehow exhausted, but he was convinced this is like a worthy goal and it's possible. And he just dragged me and Freshel many discussions until I can show you soon. I prepared like a bunch of drawings. So we got a sense of this computational DAG and how we can use this kind of very classic abstraction of any computation. It's not a new construct by its own, but it's a way of thinking about computations, which at some point it clicked.
Right.
I say the moment of clarity came with the definition of a computational scope. So we were kind of saying, yeah, you're looking at this challenge, and you're looking at this challenge, and you're saying, okay, obviously it's easy to compose if everyone knows the state of everyone else, but we don't want everyone to need to compute everyone else all the time. So it's obviously easy to being sync composable if everyone is one unit, if everyone is one base rollup. But so you want to allow sync composability even though you're introducing multiple rollups. What does it mean to have multiple rollups? So each of them has to have some kind of independency of the others, right? Some kind of sovereignty. So we were aiming for a few types of sovereignty: execution time sovereignty, computational resources. How many computations would I need to do at peak time? Sovereignty over my resources. What's my state size? I don't want to be depending on the state size of others. And sovereignty of liveness, being able to prove my progress without being dependent on the proving of others. And these are all hard problems to achieve when you add composability, because once you compose, you actually read from someone else and you write
to someone else.
You have a transaction reading and writing to other entities, and you have to know what to read. And you have to be convinced without trust that it's correct. So that was the challenge, and there was an aha moment. I might get to it soon if we get to the details.
Isn't that the end goal of blockchain, right? I mean, that's what, at least for me, it's the big goal of having synchronous, composable, trustless, right? If we can create those three things, it's a massive, grand ambition for a lot of projects that's been aiming for that, right? But never been able to even come close to it.
Yeah. Some call it the programmability trilemma or dilemma. And, and I'd say that you had to solve data scalability first, because as we can see, it's not possible, probably, at least not soundly, to solve without a scalable L1. And also just a comment on scalability. It's an interesting, so in the L2 space, sovereignty essentially also means scalability. Like if each entity is sovereign for its own resources and they can still compose, and you kind of have computational scalability and also state size scalability. So it also depends on the frequency of zero knowledge proofs, but we'll get to that. You want a system which moves fluidly between states depending on some kind of incentive game, hopefully. And I'm talking about like actors like provers and transaction issuers and POG runners and all this.
Like, I want to start defining these new stakeholders you brought in this mix, right? So the first one I wanted to sort of ask you is, who really executes vProgs? Where does it sit? Like, where does these sort of sovereign programs are going to sit, right? Based on my understanding, that is deployed by the dApps itself, and the zero knowledge part is then executed by the prover, which you mentioned, right? So yeah, just I guess quickly, if you can define, where they're going to sit and sort of what is this prover network?
So I can imagine, and there's actually a POC implemented already by Hans, and kind of L2 or vProg node, which receives as input the progs it wants to be stateful on. Okay, so it's running and it wants to be stateful for prog A or for ABC. I don't know. So it goes up if it's a new time. If it's syncing for the first time, it's going to find through some peer-to-peer network entities holding the state of ABC, sync the full state of ABC at some checkpoint, probably the pooling point. And just a comment about that, the pooling point of L1 through its UTXO commitment encapsulates the state of whole L2, because for each progs there's going to be a UTXO on L1 which represents the state commitment. So if you aggregate that into the UTXO set, the single UTXO state commitment and the floating point actually attests or to the entire vProg space as well. So as a new node, you might sync and you verify that state, and then you execute all transactions since. It's just like you do on L1 catching up.
Yeah.
And then you have L1 knows about ABC, knows what the state commitment of ABC, or let's focus on A. So L1 knows what the state commitment of A is. It tracks the transactions writing to A, specifically through the computational DAG structure. And you as a vProg node can follow that and make sure you execute everything you need to, etc. And the provers would be an entity. So if you as a vProg, if you develop the vProg and you chose some kind of infrastructure for your ZK execution, so you can probably be the one composing tasks for a prover network, even an external one like an SP1 prover network or a Starknet prover network. You as an executor know everything you need to know in order, you know what you, if you can execute trustlessly, you can also prove. There's kind of an equivalence, right?
Right. So essentially these prover networks could be like sort of external networks. So it doesn't need to be that the dApps or whoever is sort of executing an app doesn't need to sort of create their own prover network. They can even bring external, like Async, right? Like they have a decentralized prover network. They can use them.
Yeah. So think about one type of vProg would be like a Solana interpreter, the Solana VM running within an SP1 program.
Yeah.
So you know how, so there's a specific protocol to how to stitch things and how to compose, so that we have a protocol for vProgs, but whatever it is, you can wrap it up in a single thing you want someone else to prove. You're still asking him to prove an execution. It's going to be a dedicated program, which is the interpreter, getting as input the user submitted, deployed ELF contract, and combining that into an execution and proving the result was something. So all of this can be packaged and outsourced in a sense to a prover network. I'm just saying that it's not that building a prover network isn't possible within this peer-to-peer network of vProgs. Probably what's going to happen eventually, but doesn't have to happen immediately.
I see. Right. Okay. No, I get it. I think I'm starting to get a very clear picture, I think, based on what I think it's still far from a very clear picture, but at least a picture. The other term you introduced here, and also on the tweet you wrote a while back, was the computational DAGs. I don't think we explained this term because this is how Kaspa Layer 1 keeps an eye on vProgs, right? That's computational DAGs, right? So what are computational DAGs and how a computational DAG is different from a normal DAG?
So you see my screen?
Yep.
Now?
Yes, I can see your screen.
Okay. So I just prepared like a board with a bunch of drawings. So I'll do like a fast computational DAG 101
Please,
course. And it's also tightly related to parallel computing. As a side note, happens to be my master's degree subject. So that's like convenient, let's say. So this small program computes the dot product between two vectors A and B, which have length n. So it's going to do the dot product or the inner product. Sorry. Start with the s equals 0, and it goes through entries I from 0 to n, and it sums up within s equals s plus the product of A at I and B at I. Okay, so that's a simple dot product program. This computation can be described in a computational DAG. And let me just zoom out a bit here. So I kind of walk through time, okay, and draw states and results, and you'll see how it folds. So the first iteration, S is 0, so I'm ignoring it. So we're taking A at 0, subscript usage here, A at 0 and B at 0, and summing it up into S. Superscript 0 means S at time 0. Okay, so first iteration S, because S is being updated. So the computational DAG needs to describe each variable at each point in time, in a sense. So A and B are never modified, but so we're only modifying S. So you'll see that I'm drawing S at 0, S at 1, S at 2. So we're doing A0, B0, summing it into S0. Then we're doing A1, we're doing the product of A1, B1, and summing it with S0 into S1. Right? You see my mouse?
Yep.
Yeah. Then we're doing A2, B2 into S2 with S1. Eventually, we'll reach Sn, right?
Mm-hmm.
So this is a computational DAG. It's a graph.
I see.
Where each variable is a vertex or a node. An edge described data flow.
Yep.
And perhaps, like in this case, there's always like two arrows into one, so it's always a binary operation. So this is a multiply. This is a sum.
I see.
I didn't write the sum, but it's a data flow of this computation. And what you can easily spot is that this is a dot product with linear depth, meaning if you look at this, I also wanted to say that this is a DAG because it flows with time. So we obviously cannot write to a variable in previous time.
Yep.
That's why there's no cycles. That's why it's a DAG. This one is linear depth, meaning if you look at the top line here, you see it has n vertices and n edges, right? So this DAG is linearly deep, meaning the depth of the DAG is n, which is also the number of vertices, more or less. Number of vertices is maybe 3n, and the depth of the DAG, meaning that depth represents the operations which must be sequential. Like I cannot compute S1 before S0, right? And I cannot compute S2 before S1. So if you try to parallelize this algorithm, you'll end up not parallelizing it because each iteration in the loop is actually reading the result of the previous iteration. So there's no parallelism enabled here.
Right. Yes. I am starting to get it now. All right. So this is computational DAG, essentially.
Yeah, that's the computational DAG. And in our case, we're going to treat, like, instead of looking at the product or the sum as an operation, we're going to say a transaction is a compute. We're looking like we're going to do a zoom out a bit. We're not going to look at the exact computational semantics within each transaction, but only like at the outer zoom out flow of transactions, reading from X accounts and writing to Y accounts. So that our computational DAG would be more high level, but the same idea. Now, I just want to do, this might do it short. We don't have to understand this code, but this code essentially is saying, okay, a much better algorithm for a dot product would do it all in parallel as much as possible. And I'll show you like how a parallel algorithm would look like. So a parallel algorithm would use another array P as temporary storage, also size n, and it would say, okay, let's multiply A0, B0 into P0, and A1 and B1 into P1. So let's do all multiplications independently. Okay, so we're storing the products within a temporal vector, and these are all independent operations. So they don't affect the depth of the DAG we're seeing now. And then we can reduce over P and sum, like, you can sum every two consecutive entries. Or you sum, like, if you have 8 entities, so you sum 1 and 0 and 4, 1 and 5, 2 and 6, 3 and 7, 4 and 8, and you write it all down into 0 to 4. So you're kind of folding. So you can do the reduce with log n depth. Just to get some intuition why computational DAGs also describe the parallelism and the amount of efficiency you can gain by having many processors. So in a sense, if a computational DAG is not deep, here in this case, it's only going to have log n depth, you can use many processors to do it in log n time. Because you can allocate P processors to do this, and then P over 2 to do this, and then P over 4. And the time it takes is only log n. So that's a very short, like, introduction to computational DAGs.
If we were to simplify it, right, for someone who's more interested in words, what sort of analogy? I guess I'm thinking of one analogy based on computational DAG, but does anything come to your mind if you were to create analogy on computational DAG?
It's kind of pouring, like, input or water into a sink and having, like, a complicated pipe system perform all kinds of operations on different parts of the water, different drops of the water in parallel, until the waters combine in all kinds of intersection points until you get the final result. It's a data flow analogy. How would you describe it?
Again, correct me if I just got it completely wrong, but that's the fun part of having podcast. You get to learn on the spot. I think the way I was thinking, it's more like if you take example of a big kitchen where you have multiple chefs, and they're all cooking, right, with shared ingredients, like it's a shared kitchen, right? So computational DAG would be a sort of chore chart on the sort of fridge, like sitting there. It knows, it doesn't actually hold the food. It doesn't, obviously there's nothing there, right? It's just a chart, but it lists who uses what, like chef A used something, chef B used something.
It's like a pipeline. You're referring to, like, a pipeline?
Pipeline, yeah, pretty much pipeline, right? It avoids, like things are happening in order to avoid sort of fights over the use of ingredients in one pantry. I don't know if it's a good analogy, but I think it's similar to your pipeline analogy you gave.
Yeah, it's a good analogy. Computational DAG describes both, like, the pipeline. If you imagine, like, I'm not sure exactly if you meant that, but you can imagine, like, few people each has its own task, and they pass their output. So each one is specialized in something, and he knows how to do it best, and it's just happening in parallel because everyone always has one item to work on, in a sense, maybe.
Yes.
That's what in my language it's called concurrency.
Okay.
But I use parallelism to say splitting the same kind of task to many micro tasks, which are very much alike. But that's just a side note.
It's good to bring some analogies, I guess, for people to sort of think about in a different way, different medium, perhaps.
Yeah. So in the specification, we look at so this is a drawing, like, of, think about two progs, A and B, each with one account, exactly. Okay, so we're calling A both the prog and the account. So I'm saying in a circle would be the state of account at some time, and a triangle is a transaction. Okay, so this first triangle here, this triangle here is just a transaction reading from A and writing to A. Okay, and T equals 3. So the state we're writing to becomes A3. And then B has the same flow of 2 transactions going from B1 to B2 to B4. I'm using different indexes because I'm kind of giving each transaction a timestamp. So that's why this is it. Okay. And then the transaction, a composable transaction, in the sense it's composable in the sense that it reads from B and A and writes to A. So what I want to highlight here, so this is how I describe a computational DAG. So we kind of, at this previous DAG, I kind of skipped, we kind of assumed, yeah, I wrote like the type of the connection sometimes. Here we created, like, because a triangle can have many inputs and many outputs, not only binary, it can be more complicated. So I'm specifying a special vertex for the compute. So circles represent account states at a specific point in time, and the triangle is a transaction. In this case, it reads from A and B writes to A. So what you notice is that the prog A will need to execute. What I want to highlight here is the asymmetry, and you'll be surprised, but it's kind of the aha moment.
Okay.
I don't know if it's appreciated, but yeah. So it's related to the aha moment. The executor of A, actually B doesn't need to execute this transaction because it doesn't write to B. So reading and writing is different. The fact that we're reading from B doesn't induce a cost on B. So there's an asymmetry here. Even though we're reading from both A and B, because we're only writing to A will need to somehow execute and know what B4 is, right? So it might need to execute both these transactions in order to understand what the input for this transaction is, in order to write A5 correctly. And this is where you get so transaction issuer has the flexibility of where it brings. So assume B1, maybe I should try and
can you draw now, Michael? Is it possible to draw?
Yeah, I'm trying. Wait 1 second.
Sorry, while you're drawing, I'm just sipping on my coffee. Thank you.
Yeah, sure. So 1 second. Yeah, so now we're drawing. Okay. So this transaction might provide a witness to the state of B at time 1. So it's actually assumed that at time 1, L1 already knows about a proof attesting what the state of B was at time 1. So there's some kind of proof. So as a transaction issuer, I can provide a witness at time 1 for B. And then what it means is that A, in order to execute this transaction at time 5, it needs to verify the witness at time 1, and then it needs to execute this, and it can trustlessly know what the state of B4 is and execute its own transaction. Later, eventually, it might need to wait for B to prove the state in order to stitch proofs. Or if B wouldn't be live for some reason, A can still prove on his own this path as well. Because like I told you before, if you can compute something, you can also prove it.
So B1, B2, B4, right? These are individual vProgs.
It's vProg B, and at various points in time. At time 1, it has this, it had value equal 18. At time 2, it had for some reason value equal
some
72.
different state change essentially happened during different time.
Yeah. So in order to execute 5, A needs So first, like I told you, 5 doesn't induce any cost on B because B doesn't need to write at 5, so it doesn't need to execute it. But A needs to.
Oh, I see. So
A
the B,
needs to go back and execute stuff B did before.
I see. Yeah, okay. Because the B doesn't need to know the state of A, essentially.
Right.
But A5 needs to know A1, A2, A3. Is that fair statement that A needs to know all the states?
So it depends. If someone would bring me a witness to B here,
Yeah.
if time 2 would already be proven, so a witness can be shared for time 2, and then I wouldn't need to execute this one. I would only need to execute this.
Oh, I see.
So depending on the witness and how recent the witness I'm sharing is, I'm inducing a computational burden on A. As a transaction issuer, there's a specific cost for A in order to allow this composability. And the cost can be driven from the computational DAG you're seeing. So your computational DAG shows you the dependencies. And then you can use witnesses shared and compute exactly what A would need to execute in order to actually execute 5. So there's a computational scope for each transaction.
I see. Yeah.
From the point of view of a specific prog. And what we're doing is we're going to have L1 not operating these state transitions himself, but he is going to maintain the CD metadata CD with timestamps and the exact dependencies. So L1 will know exactly what the burden of what's the cost of transaction 5 on prog A. So it can regulate it and make sure that A doesn't exceed its limits.
So I see. So this computational DAG is going to sit on the layer 1. So layer 1 knows a lot of the detail it needs to know, including the gas and a few other things, right?
Yeah. Each transaction would have like essentially a gas commitment.
Gas commitment, yeah. So L1 in a way tracks all of this through computational DAG. Yeah.
Which is like the thing I described before as the cost in order to allow composability with sovereignty. L1 needs to, this would be the cost. If you think about it, this DAG has the same size, complexity-wise, like the transactions themselves, because transactions themselves also describe their dependencies. So it's not it's the same order of effort you had to do before, in a sense. Obviously, there's an overhead here, but it's not like a new dimension of overhead.
No. So what can what can then layer 1 do? What can it do? It's tracking this computational DAG. Does it have any abilities to use this computational DAG data in some way or shape or form? Like can it use this in some capacity?
So it has two significant roles. It's providing service with. The first one is computing the computational scopes I showed you here for each transaction, for each prog it's writing to.
Yes.
And regulating it so it doesn't exceed the computational throughput expected by each prog. So that's a very important role as a regulator. And we can go back to this later, and I'll show you that depending on the frequency of zero knowledge proofs, this either converges to a one fat L2, because think about it, if proofs come once a day. So you can imagine that eventually everyone is going to need to run everything else, more or less, in order to compute the state from the last proof. You'll have to go through multiple routes of data flowing through every other entity probably. But that's just going to mean the system will converge to one fat L2, where each vProg needs to compute everyone else or not compose.
Or not compose, I see.
And if you have sufficient frequency of zero knowledge proofs, which we'll get to that maybe at the next stage. So this breaks down. The mess is entangled, untangled, and dependencies become shallow in scope, and the system scales, essentially. So there's an incentive for a vProg prover to prove things more frequently if it wants to be composed with more cheaply.
I see. So that's the regulation part done by the layer 1, essentially.
Yeah.
Yeah.
And then another role of the CD, we should, by the way, move to this more abstract.
Please.
I wanted to say something. Yeah. Slightly more abstract, not much. But the other role of the computational DAG is creating, it's going to be actually a hashable entity, meaning each vertex in this DAG is going to be a hash of its parents, so to speak, or predecessors, and its own content. And that's required in order for the L2 entities to be able to stitch proofs together. It's kind of, think about it as a guideline of how to stitch. So the CD commitment shows you what your dependencies are. So you can actually, if you have proofs for each transaction in this DAG, if you have a local proof proving that condition on these inputs, this is the output. So all you need is to stitch them together according to some skeleton, according to some source of truth of how to compose. Maybe too much for now, but yeah. So the CD, that's kind of, if you look at the vProg spec, you see a stitching algorithm, and the CD commitment is used to guide the L2 of how to compose proofs from multiple sources. Okay, I just wanted to get to this one, which is a bit higher level. So here I'm drawing like 3 programs, each like, without giving a name, each vertical here is like a specific program, usually only operating with on its own.
Right.
And okay, let me move my. So here there's a first point of composability. And this means that, assume this is A, so an A now has to compute this in order to know how to update the state here, okay? But the green one has no idea of the state of B, yet C is independent. But then we have a transaction reading from all A, B, C, and writing to A and B, okay, at time T. So this transaction, I just want to highlight that what it means for A, the scope it needs is now reduced because he already needed this. He only needs this one, the remainder. And for C, he would need all of A and B in order to compute this new transaction. Just highlighting that the scope is
I see, for
point of view dependent.
Yeah.
Yeah, we want L1 to track this and give special care to each prog and regulate. Okay.
Right.
There's one last drawing I made, which is even a little more abstract, which is related to the proof frequency. So we might come back to this if you want to ask more questions first, but this is what I want to show you. I want to say something about the frequency.
Yeah, please. Yeah.
So it's the same idea. Each vertical is like a specific prog, just operating on its own. And then we're drawing a line when there's composability between progs. Okay.
Okay. So can I define this quickly? Sorry.
Yeah, sure.
So each vertical circle represent one prog. So you know each line has 1 to like 10, let's say 10 progs, right?
No, each vertical. What I mean is, this is a prog.
Oh, this is one prog, I see. So each vertical is a prog, I see. Not each circle is a prog.
Yeah, and time goes like this.
Okay, I see. Got it. Right. So, and only at one time, so maybe it's t plus 3, you need to be composable with a different prog, right? So that's the line you're drawing from left to right. So I see. I'm with you now. I think I understand. So there are 1, 2, 3, 5 progs.
So I'm simplifying and avoiding I'm not drawing lines which are local to the prog. That's just represented by the vertical line, the fact that the circles are aligned.
Mm-hmm.
And I'm only drawing like an edge in this DAG when there's composability. It's some kind of composability. So and F would be like the horizontal lines representing, like, think about it like as if everyone proves their state at this point in time. So we're assuming like some global F where for simplifying the discussion, but it's not it's not any conceptual relaxation. I'm not giving myself too much here. It's just assuming that the system has a zero knowledge proof for its state at each F steps. So if you take F, so let's assume some kind of sample rate where this a composability edge is drawn, let's say every 5 seconds, okay?
Yeah.
And just choose from random for 2 progs, there's composability between them now. So if let's call that time S. So we have S, which is the frequency of composability, and we have F. So if F is much larger than S, that's what I described before. There's going to be a mesh or an entanglement of dependencies where eventually it cascades, and you have to execute everything else, because even though you're only reading now, A is reading from B now, but B 10 steps ago was reading from C, and then C was reading from H. And because the proof frequency is not frequent enough, no one can bring a witness. People can only bring a witness for the previous proof time. So if a lot of time passed since, you eventually end up in a situation where everyone needs to run everyone else in order to compose. But as you take F closer to S, it breaks down. So on a very high level,
So just quickly, F is frequency, which we're discussing, and the S is the time, right? So if S is very close,
S is like the average time between composability events.
Yeah.
And F is the average time between proofs.
Between proofs, I see. So if it gets very close, then it breaks down.
Yeah.
Right.
How close?
How close, yes.
So surprisingly, I don't know if it's surprising or not, it doesn't need to be too close in order to gain an efficient system. And this relates to a very famous result in graph theory. So I don't know if you want to hear about it or
not. Why not? Let's go.
Let's go. It's not too long. So
sure.
So I happened to prepare this. So let's now imagine we're only taking let me choose another color. Let's focus on such an episode.
Yes, please. And can you please also, Michael, sorry, could you please zoom in a bit, please? Yeah. Oh, that's better. Yeah, thank you.
So let's focus on the red rectangle and focus on one F episode. So F can be, we can play with F later, but F, we're looking at this specific episode. So if I want to simplify things, I can create like I can reduce this. I can look at this as a graph. Now, not a DAG anymore. This is just a graph. And each dot represents a prog. So A, B, C. And I draw a line between progs if they had a composability event within a proof period.
Mm-hmm.
So what happens is, like, okay, if I drew only 5 lines, right? So you see there's only dependencies are very small. There's only but if I add now just maybe 2 more lines. 1 second.
So ABC are progs, and the circles are these are different timelines.
No, ABC is just a name for the circle. So the circle is like a vertex.
I see. Okay.
I'm sorry. Yeah, I'm putting like a label on the circle. Yeah, and then I'm drawing an edge between 2 progs if they had a composability event between them.
Okay, I got it. Yeah.
During this period of proof, meaning there was during this period of proof. So if I drew only 5 lines, because there's like I don't know, 10 progs, sparse. So there's obviously the dependencies are not yet exploding, I'd say. But if I add just like 1 or 2 lines, you'll see that suddenly all these are connected now, right?
Yeah,
because the previous connections form into one. So there's a result in random graph theory where what's the sample rate needed in order to form a giant component in a graph? Think about this as a random experiment where I'm drawing these n vertices, and then there's a parameter where I can tune the probability for each edge. So once you go above some threshold for the probability of each edge, there's almost certainly a giant component forming, which is at the order of magnitude of the entire graph. And that's exactly the explosion point we want to avoid in our work.
Right.
So we want to cut the sampling of S before, with an F proof, before there's too much dependencies forming together. That's like the kind of idea.
Right. I think I got the bigger picture, but the detail you showed, I'll need to probably spend a lot more time on it. But
yeah, that's all. That's all you need.
Yes.
The bigger picture.
I see. So you want to just make sure that you avoid that stage when it becomes interdependent, essentially.
Essentially, I want to avoid it, or I'm just showing you that if provers have incentive to provide frequency sufficient to break this kind of structure, and it's going to do good for everyone. There's going to be more scalability and more composability. And also there's hope here, because I know the threshold behaves. There's an interesting observation where below the threshold, even though it's pretty high, there's no giant components. There's only components which are logarithmically large. So we don't need to have proofs every second for having an efficient system.
What about the other side of the equation? The incentives for the provers, because the proving is not a cheap effort either, right? If the frequency is higher, then they will end up spending a lot of money, actually, right? GPUs, usually this 4090s or whatever GPUs they're using now these days.
It's only about a prover needs to prove everything that's happening anyway.
Right.
So the cost of proving every minute versus proving once an hour is related to there's a constant cost for each proof, which is independent of the computational the computation length.
Okay.
And that's where there's say I tell you that an average transaction has a cost of I don't know, 10 units. Like each step has a cost of a unit. Okay, but there's a minimum for a proof, for generating the proof. There's some constant C1, I don't know, 100 or something. So obviously it makes sense to prove at least 100 transactions together, not prove every transaction, because if you prove every transaction, you pay too much for that constant. But it doesn't need to. But the difference between having a proof every day or every 10 minutes or 1 minute isn't that big.
Okay. All right. I thought it was I thought it was more like if it's required for system to not break, you require every second, versus the prover wants to do every 10 minutes because they can batch more transactions, especially early stages.
Assume there's some gas, someone is gaining for more traffic, right? If you're having more transactions, if you can support more transactions, you get more fees.
Yeah.
Maybe the exchange, maybe the DEX, maybe, yeah. So there's someone with incentive which created this prog that wants more traffic. So that someone should be wanting to pay. So because frequent proofs allow more traffic, because they allow more cheap composability,
Yep.
so as they allow more operations, so there's more gas and more fees paid by the users. So that's a strong incentive for more frequent proofs. So the issuer or the prog owner has an incentive to pay a prover more often because he's going to get more fees, for instance. So that's how I kind of see it.
Essentially, right? It's up to them to decide, and they're free to decide in their own will how much they're willing to pay based on their own business model, let's call it.
Exactly. Yeah. Sovereignty of the service provider. I'd say that's
cool.
That's what someone is aiming for.
Yeah. I think so. If I'm the owner, I would want to have my entire sovereignty. I don't want to be dependent on external players.
It's directly related to the 100 BPS vision. Like if you think about it, 100 BPS aren't interesting in terms of speed. Like 100 milliseconds block time is already fast enough for any human. So what do you start getting from 100 BPS instead of 10 BPS? You can say a sentence like, you only need 1% of the hash rate to mine a block every second. That's a powerful sovereign statement. So it's related.
It is indeed. Michael, sort of off topic, little bit question. I thought I'll ask you now. I do have a couple more. I know you've gone quite deep, but perhaps more, rapid fire, let's call them. I wanted to ask this recent term I heard, which is, vProg of vProgs. What do you think of that? How do I sort of conceptualize it for myself? I don't know if you come across this, but yeah, what's your take on that?
That's an interesting question. I think we actually spoken about it one way or another several times, because I've mentioned like the vProg space is a one-dimensional space. So having a vProg of vProgs is kind of not that. And I've been thinking about this actually, and technically it doesn't really fit in, because as far as I understand it, it's kind of a framing of okay, let's group together this special set of progs into some entity. And I don't really understand what this entity is on a technical level. Why? Because in this design, the design is based on the fact that L1 is going to regulate the computational costs for everyone. Essentially, there was a word I didn't say it. It's based on on-site execution, meaning each prog is going to trustlessly execute all its dependencies, which is why we need L1 to regulate them, right? And how do you do on-site execution? You need to be able to access everyone else's progs. So the prog space, the contact space, should be like well-known. We need like some kind of system for data availability for all the prog space, okay? So I don't mind thinking about it even in L1 holding all the progs, actually. If that's a bonus point for L1 being L1 more, so be it. And if that's, anyway, you need some consensus about the prog space and the data availability. So all progs need to be available to everyone else so they can execute it.
Right.
So a prog is either that, even if you have a prog within a prog, meaning someone deployed a smart contract into another prog. So if that smart contract is a prog itself and known in the program space, data availability. So what's the meaning of the grouping? It's just another prog. If that contract isn't a prog but data, so what's going to happen is that the designers of such a system will realize that they need to share this contract as data with witnesses each time it's being composed with. It's like anti the design in a sense, because if the contract is just data of some master prog, then it has to be shared more frequently each time it's composed with. That's because that's how the system ensures sovereignty. So you have to choose either it's a data and then there's going to be costs to doing that. No one can stop it from happening because a vProg is a self-contained system. But if you do that, you'll pay costs because the system wasn't designed for it. Whereas if this prog is actually just a first-class citizen in the program space, I don't see the meaning of this rectangle you're drawing around this group. I don't understand what it means. To me, it's more about the infra, ZK VM over infrastructure being the template. So you can say all these progs share the same infrastructure, but they're not unique. There's no special treatment between them for composability. They're all still on a flat L1. That's how I see it. So it doesn't compile to me. If I have to summarize, the term prog of vProgs doesn't compile to me as an author of the vProgs paper.
Yeah. So you cannot compile that it's even physically, technically possible or feasible.
It's technically possible. You have to choose what you're doing and then explain the meaning of it. I don't understand the meaning.
Right. Okay. All right. Something I want to come back.
Thanks for asking about it, actually.
No, I think it's important.
Something that's been on my mind.
Thank you. And I think for me, it's important for, like, when you're building an ecosystem, I think it's important people understand different sides of the ecosystem. That's why sort of we went through a little bit of the incentive for the prover, right? We went through computational DAG. These are sort of new, I think, lingo for the Kaspa ecosystem, and along with this vProg or vProgs, like prog of progs.
Okay, great.
Anything? I do have one wrap-up question, one more, perhaps the second one. But anything we missed on the vProg side? I know we've done 1.5 hours so far. Anything from your perspective we've missed so far that we haven't covered off?
I think we touched briefly on most important questions. Like we touched on the computational scope notion and the regulation of computational throughput. We touched on the CD commitment and how it can guide stitching very briefly. We touched why pruning, why this is all prunable in a sense. Like I described to you how a new user can sync from the latest pruning point, doesn't need to re-execute everything, assuming there's proofs. There's also, by the way, there's an analogy I wasn't mentioning just for the advanced listener. You can think about, if you look at the computational DAG, you can think about a ZK proof as a compression operator taking a bunch of a whole subset of the bottom of the DAG, unproven DAG, and compressing it into a single vertex, which all the accounts belonging to this prog can be verified against. So it's kind of compressing information and compressing dependencies. So it's also, if you think about it in light of the frequency diagram, so if the compression happens frequent enough, the dependencies don't explode. One more thing we didn't touch actually is had things that more technical that have been discussed also in R&D recently, like provable metering, and also how to actually compose a transaction which writes to multiple entities. Because in the simple diagrams, I only showed you like reading from someone else, but writing to someone. And actually, the more complex cases where you have to you make a CPI call, or cross-program invocation between progs within the same transaction, and how you allow two provers to prove both sides and still stitch them. And that's a whole more lower level mechanism. But doesn't add any complexity. It's a conceptual discussion. I'd say that. So it's just a detail you have to show how you solved, and it's actually not detailed enough in the yellow paper currently, but it's being actually worked on by Fleischer now. And yeah, that's one thing I didn't touch. But yeah, more or less, I think we touched a lot of the high level, a lot of the intuition,
Yeah.
It was a good walkthrough.
Great. Yeah, I do agree. I think I did start reading on the stitching side, but I didn't get myself around it fully. I think I need a bit more time before I can even have that discussion. And I think I do have a lot more questions on the frequency bit also, the proving frequency bit, perhaps for a different session. But I guess if there isn't...
Perhaps for when we have more numbers.
Yes. Perhaps for when we have numbers, yeah. All right. If there is nothing else, then I do want to have a wrap-up question for you. And I know you gave me 1 hour, 40 minutes. So we're almost there. And I know that you haven't eaten. So I do apologize to keep you here.
No, it's okay.
So just a wrap-up question then. We all agree, and perhaps, we think vProgs are going to be game changer, especially for DeFi, which is a huge space with the crypto, right? So from my perspective, what I wanted to ask you is, what can Kaspa community do to participate in this upcoming dawn, right? What are the things the community members can do, right? You're doing your part. We're doing our part. What can people do?
So obviously education. If more and more people understand deeply the concept, they can pass it on more truthfully on a higher level, even if they don't necessarily explain it in full to everyone else. So what we're doing now, there's also Jonathan made a call for us, for some of the devs, to actually try and imagine how the SDK of the system is going to look like. Like if currently it's being built from the bottom up, so also trying to describe it top down based on strong intuition of the later coming requirements. But you can also already think about a developer SDK or a standard library a developer writing a program needs to know and use, and what the user side would look like. So if we succeed in providing some kind of such SDK or illustration of an SDK, the community can start understanding what it means. And like Jonathan also mentioned, is like the sovereignty has a meaning. That it's sometimes much easier to enter the system where everyone runs everything for you. So you're kind of with everyone else. So you're suffering from everyone else, like the noisy neighbor. If you're a smart contract with low activity and someone else high activity, you're suffering because you have to execute all his transactions all the time. That's where we want sovereignty. But sovereignty also means you as a stakeholder, or as long as you want, if you have enough stake at this prog, so you have to be one of the people maintaining it and running it and making sure it's live, because other entities can proceed, can make progress without you eventually. So you can't die, but you have to have the correct incentive and ownership. So it's a mindset of sovereignty, which is also has some obligations. It's obviously the more correct way to design distributed systems.